Okay, we're going to continue on here. So last time I think we finished up talking about stoichiometry and limiting reagents. So now we're going to move on to gases in this chapter, chapter 13. So let's talk about first off what are typically gases under normal conditions. And when we talk about normal conditions, usually that is 25 degrees Celsius. That also is usually a pressure of 1 atmosphere. And under those conditions, ionic compounds usually do not exist as a gas. And that's because ionic compounds obviously are made up of ions, which are held together by really strong electrostatic attraction, which is that positive negative attraction. And because as a really probably one of the strongest sort of attractive forces you could have, it pretty much will not break apart and go into the gas phase. You could pretty much heat the heck out of it and it will actually start to melt before it will jump into the gas phase because it's held together really, really strongly. Like some of those earlier on experiments where you just kind of threw everything into like an evaporating dish and you evaporated off the water. You were left with like a residue, which is the ionic compound. It did not go into the gas phase as you were heating it up and sort of boiling off the water. And that's because its sort of boiling point is super high and a lot higher than the water, which is only 100 degrees. And you were able to boil off the water and separate out the water from it. Now, molecular compounds are a little bit different, and molecular compounds are sort of covalently bonded compounds. These are guys that are sharing electrons. And because they're sharing electrons, some of them actually are just gases up front, like carbon monoxide, carbon dioxide, hydrogen chloride, ammonia, and methane, which is the gas that comes out when you light your Bunsen burner. But the difference between an ionic compound and sort of a molecular compound is it is actually much easier to kind of convert a molecular compound into a gas than it is an ionic compound. And even though a lot of molecular compounds are actually found as liquids and solids under normal conditions, you can much easier convert those guys into a gas than you can an ionic compound. Probably the easiest example that we're all familiar with is water. And water is a polar molecule where the hydrogen is more positive, the oxygen side of water is more negative. And when you have multiple water molecules together, say in like the liquid phase, if you will, they are actually bonded to each other through that sort of opposite attraction. The positive side of one water is attracted to the negative side of another. This type of bonding is what is referred to as hydrogen bonding. And hydrogen bonding is a type of what is referred to as a intermolecular force. And an intermolecular force is the force that holds basically these two molecules together. So it is the force that holds one molecule together with another. As we'll talk about, the basic way that works is the positive side of one molecule is attracted to the negative side of another, and that bond is what holds that together. And that is different, an intermolecular force, than an intramolecular force. So if you took just one water molecule by itself, it has covalent bonds where they're sharing electrons between the oxygen and the hydrogen on each side there. These covalent bonds are what are referred to as intramolecular forces. That means within the molecule. So that force is what holds basically the molecule together. So like covalent bonding, sharing of electrons, ionic bonding, electrostatic attraction, those are intramolecular forces. And intramolecular forces, which are the forces that holds one individual molecule together, is always much stronger than any intermolecular force, which is the force that holds a couple of molecules together. And we know that from this example because if you did heat water up in the liquid state, the first bond that would break is actually the hydrogen bonding bond there, the bond between this water molecule and this water molecule. And that will allow each of those water molecules, for example, to go into the gas phase. We know the opposite doesn't happen because if you were cooking some pasta and you're boiling some water and the intramolecular forces broke, you would produce hydrogen gas and oxygen gas, which is not great if you're boiling water because you probably won't get to the pasta part in that case, right? As you set hydrogen gas on fire before when it kind of barked and stuff like that. So we know that that doesn't happen. So this really intermolecular force that holds a molecule together with another molecule is much weaker, and a lot of molecular compounds are held together to each other that way through these intermolecular forces. And again, the sort of stronger that intermolecular force, the higher something like the boiling point would be. The weaker that force, the less the boiling point would be. For example, we take something like methane. Methane is actually a nonpolar molecule, and that means that it basically has no charge. And the intermolecular force that nonpolar molecules use is what is known as dispersion forces. And dispersion forces are probably the weakest intermolecular force you could have, and they are like temporary, super weak forces. And that's why when we look at something like methane, it is in the gas phase. A lot of organic compounds are nonpolar, so methane, like propane, butane, those are all gases you may be familiar with. And that's because, again, they're held together by really, really weak forces, which means they're not going to stay together pretty much, and they're just going to break apart. That's also why when you take organic chemistry, they stick you in a fume hood when you do experiments because a lot of organic chemicals are very volatile, which means they could go into the gas phase super easy because they're held together by these really weak forces. You could have something that's in a liquid and it'll just go into the gas phase really quick by just sitting there if you open the lid. And obviously a lot of that's flammable, which they don't want a flame near that, so they usually stick you in a fume hood. And also they don't want you inhaling it, right? Because it could go into the gas phase really, really easily. So the general rule is if there is a really strong intermolecular force, then it's really less likely that that thing will basically be in the gas phase under normal conditions. If those guys are held together by really weak sort of forces, then it's a pretty good shot that those things would be found as a gas under normal conditions. Any questions on that there? All right, so some things that are gases definitely that we should be familiar with. We have our hydrogen, nitrogen, oxygen, fluorine, and chlorine. So a lot of our diatomic molecules that are elements are going to be gases under normal conditions. Ozone, which is O3, is a gas. And our group 8 on the periodic table, which is our noble gases, are also obviously gases. They are monoatomic gases, which means they typically come as ones, as opposed to like hydrogen, nitrogen, oxygen, they come as twos. So on the periodic table here, again, pretty much this is where you're going to find your normal gases sort of located. Now, there is a difference when we talk about a gas versus a vapor. And when we refer to something as a gas, usually that means that that particular substance is found in the gas phase under normal conditions. Now, a vapor is actually different than that in a sense. It is basically the gas form of something that is actually normally found not in the gas phase, like as a liquid or solid. Probably, again, the best example is water. Water is a liquid under normal conditions, and when it goes into the gas phase, we usually refer to it, for example, as water vapor. Also why you looked up perhaps the vapor pressure of water when you did the gas experiment. We don't call it water gas, just sounds funny, but we refer to it as water vapor. So when we talk about a vapor, again, that's usually something that's currently in the gas phase, but normally is not found in the gas phase, but can be converted. But something that is considered a gas is usually always in normal conditions found in the gas phase. Now, one of the most popular sort of characteristics of gases is pressure. And we do live at the bottom of the ocean where, again, most of air is actually nitrogen gas, followed by oxygen gas and 1% other gases like argon, carbon dioxide, and whatever other things you're smelling or inhaling, depending on what air you're breathing at the current moment. The density of air does decrease very rapidly with increasing distance from the Earth. One of the most measurable properties of a gas is its pressure, and the pressure is related to collisions. So as gas molecules are obviously flying around, they are colliding with things, and the collisions are directly related to the pressure we associate with the gas. So the more collisions, the more things collide, the higher the pressure, and vice versa. The less times they collide, the lower the pressure that we see. So sort of directly related to the pressure associated with the gas is really the number of collisions that occur. If it becomes a situation where there's a lot more collisions happening, usually with the walls of the container, for example, we will see an increase in the pressure. Now, when we talk about pressure, there are some common units. And one of the ways that we measure pressure is with a barometer. And a classic barometer, not the digital one that you have in the lab there, not even the one hanging on the wall anymore, but a classic barometer used to be a pool of mercury. And in that mercury pool, you had like a glass sort of tube in there. And what would happen is as the atmospheric pressure would exert on the pool of mercury, the mercury in the tube would actually rise. Mercury is one of those weird sort of substances that actually has a reverse meniscus. Actually, will look like that rather than the normal U-looking meniscus if that is mercury. And you would actually read from the top of the meniscus here is typically where you would read it. Now, the barometer was invented by Torricelli there, and probably the three common, most popular units of pressure that you come across is an atmosphere, which is 1 atm, a torr, named after, I'm assuming, the guy invented the barometer there, and a mmHg. An mmHg is a millimeter of mercury, and that's because in a classic barometer on the side of that glass tube was essentially a ruler. And you would take the measurement like you were reading a ruler, a lot of times in inches of mercury, sometimes in centimeters of mercury, but most commonly millimeters of mercury is basically where that unit comes from. The relationship between a torr and millimeters of mercury is basically a one-to-one relationship. So if you're converting between those two, all you have to do is basically just change the units because it'll be the same number. It's a one-to-one. The relationship between atmospheres, millimeters of mercury, and torr. 1 atmosphere is equal to 760 millimeters of mercury and 760 torr. That 760 number is obviously your important number. If you have atmospheres and want millimeters of mercury or torr, you're going to multiply by the 760. And vice versa, obviously, if you have torr or millimeters of mercury, you are going to divide by the 760. And that will get you to atmospheres. As those guys will cancel over there. Now, again, like I said, probably these are your three big units of pressure. There definitely are other units. There is PSI, which is pounds per square inch, something like 14.7 PSI in an atmosphere. There's also pascals, kilopascals is sometimes used. And also, for example, a bar is also used as a unit of pressure. A bar in an atmosphere is pretty much almost a one-to-one conversion. It's like 1.01 to 1, so it's super close to each other in terms of the conversion factor there. Here's a much nicer picture of barometer. Again, you can see kind of that reverse meniscus that happens up there. And again, usually there's some type of ruler, and you can take a measurement in millimeters of mercury or convert it to millimeters of mercury. As I mentioned before, a pascal is also a very common unit. There's 101,325 pascals in an atmosphere, or 101.3 kilopascals. And as you can see there, 1.01 bar equals 1 atmosphere, almost a one-to-one conversion, just slightly off. And there's our 14.7 psi equals 1 atmosphere. So again, some other common gas units, and you probably should be familiar with them, I imagine, but usually the big three is the one we see the most, but occasionally these guys do pop up. A lot of Pascals in chemistry usually, but other places you sometimes see it. All right, so let's talk about some gas laws. And when we talk about gas laws, there's really sort of three variables that we deal with: pressure, volume, and temperature. And when we're looking at these gas laws, sometimes we may keep something constant and vary the other. So here, the first one we're going to look at is Boyle's law. And Boyle actually studied the relationship between pressure and volume. And what he found was that as the pressure went up, we would actually see the volume go down. And that does make sense if you just think about logically the volume part of it. If you have a small volume, that means your gas molecules are pretty darn close to each other. That means there should be a fairly quick increase in the rate of collisions. They don't have to fly very far to hit the wall, basically, right? So they're going to have a lot more collisions. That's going to result in an increase in pressure. Now, if the pressure goes down, that typically results in the volume going up. So again, if you just think about it in terms of the volume, if you have a much larger volume, everybody's going to have a little bit more room to fly around in. It's going to take a little bit longer for collisions to occur, for them to hit the walls of the container. The result of that is usually you will see a drop in the number of collisions, and that's going to show you a drop in the on the pressure. And this is at constant temperature. One interesting relationship that occurs with Boyle's law is you could do an experiment where you're doing a sort of a Boyle's law experiment where you're keeping the temperature constant, and you can make a bunch of measurements of pressures and a bunch of corresponding measurements of volumes. And when you multiply those numbers together, it will always equal the same number. And that is what is sometimes referred to as a proportionality constant, which is what that little K means. And that actually means that you could actually set PV equal to each other for two sets of conditions. And if you do that, that gives us what we currently usually refer to as Boyle's law. P1 times V1 equals P2 times V2. Once again, constant temperature here. And again, pressure goes up, volume goes down, vice versa. Pressure goes down, volume goes up. Now, in terms of units here, it really doesn't matter what the units are as long as they are the same units on both sides. So whatever the pressure unit is on the left needs to be the same pressure unit on the right. And whatever the volume unit on the left is obviously needs to match the volume unit on the right so that everything cancels out. So it doesn't really matter which one it is in terms of units, but they do need to sort of be the same units on each side. So this is sort of like a before and after type situation. And this is what we see when we look at a graph of sort of Boyle's law. Here at a much smaller volume, we have a much higher pressure. And again, as the volume increases, we get a lot more space for everybody to fly around in, and we do see that the pressure starts to drop basically as a result of that. So you can see here the pressure dropping as the volume is increasing and going to the right. Again, more room, less collisions, longer for collisions to occur, drop in the pressure. All right, so let's try one here. An inflated balloon has a volume of 0.55 liters at sea level, 1 atmosphere, rises to 6.5 kilometers where the pressure is 0.4 atmospheres. Assuming temperature remains constant, what is the final volume of our balloon? So take a moment there. Okay, so let's take a look at it. And obviously at this point, we have only one gas law to choose from. That's probably the best choice, I assume, at this point. But a lot of times it's a really good idea, and when you're doing gas law problems, just kind of pull out the information. So we have a volume that's 0.55 liters. We have 1 atmosphere, which is actually a pressure. 6.5 kilometers is just useless information in this case. We then have another pressure that's 0.4 atmospheres, and we are looking for a volume here. So again, just kind of labeling everything, it should really kind of point you in this direction, as it kind of looks like the only one that obviously has all those. The ones and the twos doesn't really matter as long as you keep the numbers that go together. Usually people just kind of go in the order in the problem. So we'll call those ones, call those twos. Unit wise, we're okay in terms of pressures. They're both the same unit. So in this case, we have our P1 V1 equals P2 V2. A reminder that when you have all these gas laws, the quick way is just to go opposite locations. So although it's not written as a fraction, whenever you move something to the other side, it ends up in the opposite location. So in this case, we're looking for V2, which means P2 needs to go to the bottom, and that would give me P1 V1 P2 is equal to V2. So again, that's just a quick way to rearrange things. You just move it to opposite location. If you move it to the other side, by the way, whatever you're solving for does need to be on top by itself. Otherwise, if you leave it on the bottom, you're doing 1 over it, and that's not really what you're looking for. So we'll put our numbers in. We'll go with 1 atmosphere. We will go with 0.55 liters divided by 0.4 atmospheres. Atmospheres will cancel. That is going to leave us our units here in liters. So we'll take basically 0.55 divided by 0.4. Going to get us 1.4 liters as our answer. Any question on that one? Also, sometimes people do rearrange or invert numbers when they're doing gas law problems. So what you want to also think about is maybe that relationship we talked about. So here we see our pressure went from 1 to 0.4. Our pressure went down, which means our volume should go up. And it went from 0.55 to 1.4. So it did at least go up. So probably maybe a good shot. We didn't mess up the calculation in that case. If you did it and you got less than what you started with, you should know that that shouldn't be the case. So sometimes it's good to think about, does your answer make sense? Any questions on that there? All right, continuing on then to this one, no, to the next one, which is Charles' law and Guy Lussac's law. And Charles' law and Guy Lussac's law dealt with a couple of different things. Charles' law dealt with volume and temperature, and he kept pressure constant. Guy Lussac's law dealt with pressure and temperature, keeping volume constant. So let's talk about what's happening in each of these sort of situations. We'll start with Guy Lussac's law over here. And in this particular case, it is P1 over T1 equals P2 over T2. This is again at constant volume. So in this particular case, what's going to happen is if we have a gas in this container, the volume is fixed, it's rigid, so it will not move. If I increase the temperature here, what is going to happen basically to that gas molecule? It's going to start to pick up energy because you increase the temperature, which means it's going to start flying around a lot faster, which means it's going to cause a lot more collisions that's going to occur. So what we would see here is if we increase the temperature, we would expect the pressure to also increase as well because the volume is basically fixed and not moving. Opposite is true. If we lower the temperature, our gas molecule is going to be flying around a lot slower. Dramatically drawn slow moving gas molecule. So it's going to cause obviously less collisions in that case, and we would expect basically our pressure to drop down. Any questions on that there? Now, what happens with Charles' law? Well, Charles' law looked at a similar sort of relationship. He was V1 over T1 equals V2 over T2. This is at constant pressure. So what's going to happen in this case is as we increase the temperature, we are going to get this situation going to occur. It's going to start flying around a lot faster. The problem is, as we saw to the right there, if the volume does not move, the pressure is going to go up. So here we actually want to keep it at constant pressure. So what happens is, as these gas molecules are flying around faster, we actually will, dramatically drawn, increase the volume. And even though they are moving faster with that extra volume, it's going to keep the rate of collisions basically the same. And that's what keeps basically the pressure constant. The volume here is going to adjust to allow the number of collisions to be the same, even though they're moving faster. And we would expect our volume to increase as you increase the temperature. Vice versa as well. If you lower the temperature, once again, our gas molecule is going to be moving around slower, which means if the volume doesn't change, we would expect the pressure to drop like we did on the right-hand side. So what happens in this case, actually the opposite. It goes from bigger volume to smaller volume. So it will shrink the volume in this case. And the result of that is, even though they're flying around slower, they've now been shoved into a smaller container, which means the rate of collisions will basically stay the same and the volume will decrease. So in this relationship, as one goes up, the other goes up. And as one goes down, the other goes down. In Charles' law situation, again, the way we're able to maintain constant pressure is the volume's able to adjust like a movable piston type of thing up and down. In the case of Guy-Lussac's, we don't have that volume adjustment, which means as soon as you raise the temperature or lower the temperature, you're going to see basically a direct impact there on the pressure is going to go up or down depending on what you do. Any questions on that there? Now, when we look at a graph here of temperature versus volume for any gas you like, helium, methane, water, hydrogen gas, dinitrogen monoxide. And if we do a straight line on this graph and take it down to the temperature point, every single line here will basically hit the exact same spot, and that spot is negative 273.15 degrees Celsius. That number should look familiar to you. That is the number we use to convert into Kelvin, right? And if we were to convert this into Kelvin, we would add 273.15, gives us 0 Kelvin, which is the absolute zero, sometimes referred to. And Kelvin obviously recognized this behavior, and that is why, and who you could think, for pretty much any gas law we have, like these here, whenever you're using a gas law, the temperature always needs to be in Kelvin. So it is pretty much a no-brainer that if you are using a gas law and you need to use temperature in it, it has to be in Kelvin. Now, even in a problem like either one of these, where they may give you the temperature in Celsius and want the answer in Celsius, and sometimes people think, well, they gave it to me in Celsius and want the answer in Celsius, so I could just leave it in Celsius. You need to convert it to Kelvin, go into the gas law, and then convert it out of Kelvin back into Celsius afterwards. So always has to be in Kelvin as you go into the gas law, no matter what the situation is, if it's a gas law. Now, in terms of volume on the left there, doesn't matter the units as long as they are both the same. In terms of pressure on the right, doesn't matter the units as long as they are both the same. So as long as those are both the same units, pressure can be either any unit, and volume can really be any unit. They do have to be the same, though. Any questions on that there? All right, and obviously 273.15 to do our conversion. So again, we have our proportionality constant, which allows us to basically do our two gas laws. And again, our Guy-Lussac's P1, T1 equals P2, T2. And again, constant volume here. All right. Let's try one here. In an experiment, 452 milliliters of a gas is used in a light bulb and it's heated from 22 degrees Celsius to 187. What is the final volume here? So take a moment and see what you come up with. Okay, so let's take a look again. Once again, if we pull out the information, we have a volume that is 452 milliliters. We have a temperature that goes with that is 22 degrees Celsius. Got another temperature of 187, and we are looking for a volume. So you could kind of almost see the correct one to choose by just labeling it right there would be Charles. Clearly no pressures mentioned, so none of those are going to apply in this case. Remember, we have temperature, so once again, it should be almost automatic, 273.15 added to each of these. That's going to get us here a 460.15 Kelvin and a 295.15 Kelvin. Here, we'll call these guys ones, these twos. So V1 T1 equals V2 T2. In this case, we wanted to solve for V2, so we need to move T2 to the other side. Once again, going to end up in the opposite location, so it's going to go up on top there. Going to give us V1 T2 T1 equals V2. Putting in our numbers correctly here, V1 452 milliliters. We actually want T2 up on top, 460.15, divided by our T1 of 295.15 Kelvin. Kelvin's going to cancel. We're going to leave us our answer in milliliters, and that answer is going to be here. About 705 milliliters in this particular case. Once again, we can kind of see if it sort of makes sense. Our temperature here went up, and in Charles' law, that means my volume should also follow. So it went from 452 to 705. So the volume did go up correctly here. Any questions on that one there? Let's try another one here. Not that one. It's the one we just did. Let's not try another one. That's the same one we just did. Let's talk about another law, and that is our friend Avogadro. He had a number, but he also wanted a gas law. Why not? Free. When we think about Avogadro, right, that is 1 mole equals 6.022 times 10 to the 23. So not surprisingly, moles, which is abbreviated with an N here, is in Avogadro's law. And that is V1 over N1 equals V2 over N2. This is actually at two conditions: constant pressure and temperature. So this is under two conditions of constant pressure and temperature. Basically, the relationship here is as the moles increase, so does the volume pretty much proportionally to it. So it increases the same way. You can basically plug and chug into this one here. Volume can be any one you want as long as they're the same. Obviously, this is moles on both sides in each case. Now, sort of a consequence of Avogadro's law is this. As you can see, if you have one volume, you got 1 mole of gas. You got 2 moles of gas, you got 2 volumes, and 3 moles, 3 volumes of gas. So again, as the moles sort of go up, so does the volume. One of the consequences of Avogadro's law in stoichiometry is you could actually do some gas stoichiometry without having to necessarily use a gas law if it is under constant temperature and pressure conditions. So let's just say, for example, here we had this equation under constant temperature and pressure, and we were starting with 5 liters of nitrogen, and we wanted to know how many liters of NH3 would we produce. So normally when we do a stoichiometry problem, as we talked about, we do a mole to mole relationship between the coefficients. And since this is under constant temperature and pressure, it falls under Avogadro's law, which means we could do a similar relationship using the coefficients, but instead of a mole to mole relationship, we could do a volume to volume relationship. So for example, we could say that for every 1 liter of N2, you get 3 liters of H2. And just like you would do a mole to mole relationship, you could do that as well. You could also say for every 1 liter of N2, you get 2 liters of NH3. And you can say for every 3 liters of H2, you get 2 liters of NH3. Once again, you could do this because it's all gases and it's under constant temperature and pressure. If it's not, you can't use this sort of relationship. So how would that help us? Well, we could basically just do a little stoichiometry calculation involving just the volume. So if I started with my 5 liters of N2, I could use my relationship between N2 and my product here, which is NH3. And I would say for every 1 liter of N2, I would get 2 liters of NH3. Liters would cancel, and I would produce, in this case, 10 liters of NH3. I could do just a basic little stoichiometry problem here without having to use a gas law, basically, in this particular case. Any questions on that there? Obviously, like I said before, you could also just plug and chug into Avogadro's law like any other gas law in this case. Yeah. As we'll talk about gas stoichiometry a little bit later on, you have to use some type of gas law a lot of times. But again, if they're under this sort of constant temperature pressure relationship and you're just interested in volume, you could kind of do this type of calculation. Again, it's basically the same thing as a mole to mole relationship. Now, putting together all of those gas laws, Boyles, Charles, Avogadro's, gives us the granddaddy of them all, which is the ideal gas law, and that is PV equals nRT. The ideal gas law is for an ideal gas, and PV equals nRT is probably the most restrictive sort of gas law that you use because everybody has to be in the proper units. So pressure has to be in atmospheres. Volume has to be in liters if you're using the ideal gas law. N, which is moles, should be moles. And T does have to be Kelvin like all other gas laws. The reason for all these guys having to be in those units is R. R is the gas constant. And R has a value of 0.08206 liters times atmosphere, Kelvin times mole. So you can see it has all 4 of those units. So if you remember at least the units associated with the gas constant, you'll know all the units everybody else has to be in there. So everything properly cancels out. Also different with the ideal gas law here is kind of like a one and done situation. You only have one pressure involved, obviously, one temperature, one volume. It's not like a before and after type of formula in this particular case. What makes something an ideal gas? Well, ideally, it is basically 2 things here. One thing that makes something really an ideal gas is the idea that the volume of the actual gas molecule in an ideal gas situation is way smaller than the volume of the container in which it's flying around in. So usually we don't worry about the volume of the actual gas itself. And if you look at a lot of problems that you'll come across, they will talk more about the volume of the container that the gas is in. And that's under ideal conditions. Really, the volume of the container is more important than the volume of the gas. You know, if you had like a big trash can, and you put just like a small little pebble in there, the volume of the pebble versus the volume of the trash can is not very significant, right? The trash can is much, much bigger. But if you took like the trash can over there, for example, and you threw like a basketball in there, at that point, the volume of the basketball is quite important. It doesn't fit as great in that volume. And that's what's known as a real gas or a non-ideal gas, which we don't talk about in this class really. You talk about it in 1A, but that's a different situation. Now, the other thing that actually makes something an ideal gas is the idea that you could have in an ideal situation multiple gas molecules, multiple types of gas molecules flying around in the same container. And the idea here is they will not interact with each other. So it's almost like they're in the container by themselves in an ideal situation. There's no interaction between one gas molecule and another. They're not like attracted to the other gas molecules. They're not repulsed by the other gas molecules. So in an ideal situation, we don't have to worry about those intermolecular forces, those attractive forces or repulsion forces. Why was that important? Well, in a non-ideal situation, which again, we're not going to learn in here, if there was some type of attraction between these gas molecules, that would kind of slow down the gas molecule, and that could affect the pressure. Or if it wanted to get away from a gas molecule, it'd fly away faster and perhaps make more collisions. So in a non-ideal situation, you actually have to take into account the volume of the gas itself, and you also have to take into account the attraction between different gases. Nice thing is, in most cases, under most pressures that we deal with, people pretty much behave ideally in terms of gases. You really don't get into a non-ideal gas situation unless you go super high temperatures, super high pressures and really low temperatures is when you get that situation occur. So everything's an ideal gas law here. Now, a couple other important things that we come across is the idea of STP, and we'll start with that. STP stands for standard temperature and pressure, and it is actually giving you a value. So when it says at STP, the temperature is 273.15 Kelvin or 0 degrees Celsius, and the pressure is 1 atmosphere. So those are the actual values that you could use. For example, if you're going to use the ideal gas law, that would be your pressure and temperature that you would put into your ideal gas law if it's under STP conditions. Now, there is a really handy dandy conversion factor that you probably used in that gas experiment. If you happen to be at STP, and it has to be at STP conditions, 1 mole of any gas you got is 22.414 liters. So that is a conversion factor that you can use at STP and only at STP. So if the temperature is not 273, pressure is not 1 atmosphere, you should not use that conversion. And sometimes people want to use it everywhere. So it is only specifically for STP conditions. Now, the good news about the ideal gas law is you could use that under any conditions you like, yeah? So it could be STP conditions, not STP conditions. You could always use the ideal gas law. So if you really don't even want to remember this or worry about it, just go into the ideal gas law. Even if it's at STP, you'll get the same answer. Just use 273 and 1 atmosphere. I guess use 273.15 here at this school and 1 atmosphere. And you'll get the same answer. But if you want a shortcut and not use the ideal gas law in an STP situation, you can use that conversion factor. Any questions on that there? By the way, that is how we get the value of the gas constant. And if we solve for R, which is a constant, that is our 1 atmosphere pressure. That's our 273 temperature. That is our molar volume of 22.414 for 1 mole. Gives us this number here. I personally go with, like I said there, 0.08206. I know a lot of books and people like to round this to 0.0821, so that's fine too. It just kind of depends. I personally go with the top one because that's kind of what they beat in my head, and I can't get it out as much as I try. That is the one I remembered here, and all these years later. Any questions on that there? All right. All right, let's try one here. Calculate the pressure in atmospheres exerted by 1.82 moles of SF6 gas in a steel vessel with a volume of 5.43 liters and a temperature of 69.5 degrees. Okay, so let's take a look. In this case, we want the pressure. We have moles, which is 1.82. We have a volume, which is 5.43 liters, and we have a temperature that's 69.5 degrees Celsius. So very quickly, hopefully you can recognize there's only one of everything, so that pretty much eliminates all the other gas laws. That means this would be pretty much the only one that's available to you. I will say that probably never in a problem will they mention the gas constant. It's just, again, a value that they just assume you know. They'll never really mention anything about it. So remember, you always have R available to you, and it is a constant number here. Now, remember that when we use this, we do have to watch out on units. So that's in liters, so that's okay. That's already in moles, so that's okay. Once again, our temperature does need to be converted to Kelvin. So we'll add our 273 to it. So 69.5 plus 273.15 giving us we'll go 342.65 Kelvin. Now I will say very common on sort of these type of problems is, although in this particular example you're already given the information in moles, it's a very common conversion to go from grams to moles in these problems. And again, in the molar mass from the periodic table is that conversion factor allows you to do it. Also, I would say super common as well, volume a lot of times in milliliters, and you got to go to liters, which is a very common conversion. Again, a reminder, 1,000 milliliters equals 1 liter. So those two conversions are very commonly used a lot in gas laws, those kind of taking grams to moles and converting that volume into liters. At this point, we got PV equals nRT. Again, it's not really written as a fraction, but if you need, you could do it like that. And here we're going to solve for pressure, which means volume needs to end up on the bottom on the other side. And that's going to give us P is equal to nRT divided by V. Putting in our numbers here, our moles, 1.82 moles. Our R, which is our constant, that has all those units. Our temperature that we converted into Kelvin, so everything properly cancels. All divided by our volume in this case, which is already in liters. And again, liters will cancel, Kelvin will cancel, moles will cancel. That's going to leave us only atmospheres left over as our unit, which is good since we're looking for a pressure. And we got a 1.82 times 0.08206 times 342.65 divided by 5.43. Going to get us a pressure of 9.42 atmospheres. Any questions on that one? So again, most common mistakes people make on this one, things are not in the right units. So you guys just got to watch the units definitely when you do that. Again, remembering the gas constant and the units to go with it will tell you basically what everybody else needs to be in terms of their units, so everything properly cancels. Any questions on that there? Oh. So continuing on here, let's try this one. Calculate the pressure exerted by 32.5 grams of SF6 in a steel vessel that has a volume of 252 milliliters at 45.5 degrees Celsius. Sulfur there, 3207. Fluorine, way over there. 19, maybe. We'll go with that, I hope. I see a number, but I'm not sure what it says under there, but hopefully it's 19. Okay, so let's once again take a look at it here. We're looking for our pressure. We have grams in this case, 32.5. We have a volume that is 252 milliliters. We have a temperature 45.5 degrees Celsius. Again, you can kind of see you have just one of everything, and we know we could go grams to moles here. So we do have N. So we do have our PV equals nRT. Again, usually never given to you is our gas constant there. And in this case, PV equals nRT. We do need to do a little bit of work here. We need to get our moles. So we're going to take our 32.5 grams of SF6. We'd go to periodic table there and calculate the molar mass of SF6. 3207 plus, we got there 6 times 19 perhaps. 146.1 grams per mole. That's going to get us here. We'll call it 0.2225. I won't round too much here. SF6. Also, we do need to convert our volume here into liters. So again, 1,000 milliliters is a liter, 0.252 liters. And like normal, a little Kelvin action on our temperature there. So 45.5 plus 273.15, 318.65. All right, we now have basically everybody in the right units. We're going to solve for P again, which will be nRT divided by V, dividing that to the other side. Put in our numbers, 0.225. I missed a 2 there, I think. Try that again, 0.2225 moles. Our gas constant, liters, atmosphere, Kelvin mole. Our temperature in Kelvin, 318.65. All divided by our volume here, 0.252 liters. Moles will cancel, Kelvin will cancel, liters will cancel. Gonna leave us still atmospheres left over. So we're gonna end up with that times 0.08206 times 318.65 divided by 0.252. 23.1, why not? 23.1 atmospheres. That's a big time pressure, about 23 times normal pressure. Any questions on that calculation? So I would say this is very common sort of conversions that you have to do in these type of problems. Grams to moles using the molar mass, volume to liters for milliliters, and obviously temperature, pretty much always Celsius to Kelvin. Any questions on any of those there? Okay. Obviously, we solve for pressure in those cases, but you can solve for any of those variables, volume, obviously, N and T as well. Now, when we talk about changes in all three variables, pressure, volume, and temperature, if we take the ideal gas law and actually solve for R, that gives us PV over NT. And if we set that equal to each other, because it equals the gas constant or the value of R, we get P1 V1 over N1 times T1 divided by P2 times V2 divided by N2 NT2. In most cases, the moles of the gases don't change if you don't open that container. So that usually reduces down to this, which is sometimes referred to as the combined gas law. And the combined gas law in this sort of basic form, P1 V1 T1 equals P2 VT V2 T2. Here, temperature, like normal, does need to be in Kelvin. Pressure on each side doesn't matter as long as they are the same. Volume on each side doesn't matter as long as they are the same. Now, we've learned a lot of gas laws, which obviously they want you to know in this class. But if you should want to just make it easier on yourself and you want to commit yourself to learning maybe the least number of gas laws possible, this is your winner right here. So this is the gas law that you should learn. Why is that? Especially if you learn this one, the P1 V1 over N1 T1 equals P2 V2 N2 T2. If you learn this version of the combined gas law, and you come across a problem where they do not mention anything about moles, they do not mention anything about temperature, or they tell you, hey, it's constant. All you have to do is come to this and scratch out what they didn't give you or told you was constant. And if you do that, that right there looks like our friend Boyle's law right there from that equation. If you learn this equation, and maybe only this equation, and you come across a problem where they don't mention anything about pressure or moles, or they tell you it's constant. You just come over here, scratch it out, what's not given to you or what's constant. And that right there looks like our friend Charles' law. If you take this guy and you come across a problem where there's no mention of volume or moles, or you're told they're held constant, you cross those guys out. And right there is Guy Lussac's law. Now you come across here and you come across a problem and they don't mention anything about temperature or pressure, and they're told they're held constant, you scratch out pressure, scratch out temperature on both sides, and there's our friend Avogadro's law. Yeah. So you pretty much can get every single gas law from this one particular gas law. All you gotta do is just scratch out what's not given to you, what's held constant, and you'll be in business. You'll probably have the right gas law to use. So if you really just want to invest your time wisely, it's good to know the ideal gas law. But basically, this is based off the ideal gas law, by the way. And if you remember this one, and really the other one, are really just this one correctly there, you pretty much can get any gas law that you need. By the way, if you can't remember this one, but you do remember this one, it's based off of that. Just solve for R. And you get PV over NT and just set it equal to each other, and you'll have basically the combined gas law. So my recommendation is I would go with those two for sure, and just scratch out what you don't need or what's constant or not given to you, and you'll pretty much have the correct gas law. Any questions on that there? All right, let's try the math maybe. Consider a sample of oxygen gas at 27 degrees Celsius with a volume of 9.55 liters at a pressure of 2.97 atmospheres. The pressure is changed to 8.25 atmospheres, and the gas is heated to 125 degrees. What is the new volume here? Okay, so let's take a look at this as we're getting to the end here. Again, we pull out the information. We have a temperature of 27 degrees Celsius. We have a volume of 9.55 liters, and we have a pressure of 2.97 atmospheres. We have another pressure of 8.25 atmospheres. We have another temperature of 125 degrees Celsius, and we are looking for a volume. So hopefully that should put you to the combined gas law. Again, if not, and you remembered what we just talked about a second ago, you remembered at least this equation. There's no mention of moles here, so all we have to do again is scratch it out. No mention of moles or grams or anything like that. So that leaves us really the combined gas law. P1 V1 T1 equals P2 V2 T2. In terms of units, these are the same, so we're good to go. Like normal, we do need to convert to Kelvin here, so we'll add our 273 to each side there. That's going to give us there 398.15 Kelvin, and over here 300.15 Kelvin. In this case, we are looking for V2, as we could call all these ones and these guys twos. So again, just quickly rearranging opposite location, he's going to go up. The P2 is going to go down, basically. And that's going to give me P1 V1 T2 divided by T1 P2 equals my V2 in this case. Again, opposite locations as they go across. Making sure everybody gets in the right spot in terms of numbers. P1 is 2.97. V1 9.55 liters, T2 up on top 398.15 Kelvin, T1 on the bottom 300.15 Kelvin, and P2 on the bottom 8.25 atmospheres. Atmospheres cancel, Kelvin cancels. Going to leave our volume here in liters, which is the only unit left, and that's going to give us 2.97 times 9.55 times 398.15 divided by 300.15 and an 8.25. You can go 4.56 liters in this case here. Question on that calculation. So again, if rearranging equations is problematic for you, which is where a lot of people kind of mess up, or invert numbers, put, T1 on top versus T2 and that so forth. Just make sure you're really careful about that. Any questions on that there? All right, we will lay it up